Thanks, Anthony. So, yeah, the last time I was here, I talked about effects of ocean acidification on coral reproduction. That was several years ago, and I've switched gears a little bit in my postdoc to look at biogeochemical processes and carbon fluxes. So that's the focus of my talk today. But thank you all for coming. I'm really grateful for an opportunity to get some feedback on some of this work that I've been doing the past year or so. We're all aware that atmospheric carbon dioxide levels are increasing, and this paper was just published last week in Nature, and it indicates that atmospheric CO2 levels are actually going to have already surpassed 400 parts per million this month, and are going to, within the next month, exceed 400 parts per million on a daily basis. And that's a worrying trend because those kinds of values haven't been seen in a few million years. So this data is coming from an infrared analyzer that's on the summit of Mauna Loa in Hawaii. And the program was started in the late 50s, in 1958. And at the time that they started the program, the values in 1958 of atmospheric carbon dioxide were around 316, 315 parts per million, which wasn't too far off the mark of 280 parts per million, which are those pre-industrial values that you typically hear. But over the last 55 years, they've gone from 316 to over 400 parts per million. And as you can see on the right, the increases in atmospheric carbon dioxide levels are very closely tracked by increases in PCO2 of the surface oceans of the water. And there's an associated decrease in the pH of the seawater that has serious implications for physiology and biology of marine organisms. So just to briefly go over what happens when CO2 is absorbed by the ocean surface waters. We emit massive amounts of carbon dioxide into the atmosphere. It doesn't all stay there. About a third of it is taken up by the surface oceans. And it does stay in the surface oceans because it takes thousands of years to be exported out to deeper waters. So it's really concentrated in that top part of the water column. And when carbon dioxide fluxes in at the air-sea interface, it combines with the water molecule to form this weak acid, carbonic acid, that very quickly then dissociates into its ionic components, hydrogen ions and bicarbonate ions. And in order to buffer larger shifts in chemistry, existing carbonate ions that are in the water column combine with these hydrogen ions that are released to try to buffer any shift. So the end result of carbon dioxide uptake is an increase in CO2, molecular CO2, an increase in bicarbonate, and an associated decrease in carbonate, a decrease in pH, and a decrease in saturation state. And saturation state is a term that I'm going to refer to a lot in this talk. So just to introduce it, it is technically defined as the ion concentration product of calcium and carbonate relative to a stoichiometric solubility constant for a particular mineral phase of calcium carbonate, which is aragonite for a lot of reef-building organisms, high magnesium calcite for crustless coralline algae, calcite for other organisms. And it can kind of be thought of as an ease of precipitation of calcium carbonate. So if your saturation state is 1, it means that it's supersaturated in the water column, and anything greater than 1 indicates a greater ease of precipitation or calcification. Anything less than 1 is a tendency towards dissolution. And over the past 10 to 15 years, there's been a lot of experimental work, both in the labs and the fields, to try to characterize the relationship or come up with better constrain the relationship between calcification rates and saturation state. So back in 2000, some of the pioneering work with this was done in the biosphere with Chris Langdon, and he looked at the calcification rate of a coral reef mesoplasm over a range of saturation state values. And up here, just for reference, are some of the typical PCO2 values. So 280 is a pre-industrial value, where they were calcifying at around 100% of their pre-industrial conditions. 390 is present-day conditions, and 560 is future CO2 ocean acidification scenarios projected for the middle of this century. So this was one coral reef mesocosm, and then that technique has been adapted to different field studies around the world, lab studies. This particular study was done in the Red Sea, and then those findings were extrapolated to over 9,000 reefs around the world to look at how global scale reef calcification will decline in coming years. And the overarching finding is that as saturation state reduces and as coral calcification rates reduce, that there are a variety of implications. Not only is calcification reducing, but we're also having a few studies coming out over the last few years that decreased saturation states correspond to increased rates of bioerosion and dissolution in corals. So since reef growth ultimately depends on the balance between your constructive processes and your destructive processes, we're really shifting that balance away from construction in the favor of destruction and shifting reefs as a whole towards a state of possibly entering a state where they're no longer able to calcify quickly enough to effectively form reefs. And that's worrisome for a variety of different reasons. We're losing reefs, which has implications for habitat loss and a variety of different marine organisms that are reef dependent, fishes, other marine invertebrates. Economic implications because of decreased or increased impacts on fisheries and tourism. So the effect on corals themselves is really indicative of domino effect or greater effects at an ecosystem or an economic level. So in light of all of this research, there's been an increasing focus on trying to develop predictive capabilities to assess when this shift is going to occur. When are reefs going to go from net calcification to net dissolution? What's the PCO2 value, the saturation state, when that happens? Is there a tipping point? And how much time do we have? And that's a very complex question for a variety of different reasons. Firstly, most of the acidification projections are based on data collected in open ocean environments. So you'll often see these graphs where they have present-day saturation state values and then what the saturation state will be 50, 100, 200 years into the future. And most of this data is collected from open ocean cruises that are collected very far away from nearshore environments. And the implications for nearshore, shallow environments that typically have a lot of biological activity and are much more dynamic are not very well understood. So we try to fill this gap by doing laboratory and field observations to try to understand future scenarios in more dynamic environments. But laboratory experiments obviously often suffer from decreased ecological complexity. Field observations, you have the ecological complexity, but you can't live in the field, so you're limited by sampling size. So there's a variety of different constraints to our understanding. Furthermore, we're also starting to realize that as opposed to these open ocean conditions, which tend to be very stable because they're in equilibrium with the atmosphere, nearshore environments have huge swings in carbonate chemistry. Like this, for the example, this study that was done by Emily Shaw and Ben McNeil on Lady Elliot Island showed that over the course of days, you can have PCO2 values that range from 100 parts per million to 1,400 parts per million over the course of days. And the associated pH values are 7.6 to 8.6. And so there are already huge shifts in carbonate chemistry that these organisms are seeing on a daily basis. So when you're trying to contextualize 0.1, 0.2, 0.3 pH unit change in open ocean waters to a reef environment that sees these huge swings anyways, it's a complicated question. So some of the objectives of the study that I've been working on over the past year are really in the context of all of those limitations in the previous slides. So the main one is to try to better characterize current trends in seawater carbonate chemistry and coral reefs. So we know from Emily's study what happens on Lady Elliot Island, and Jack Silverman has done some stuff on One Tree Island. Are those reefs indicative of other reefs? Are they indicative of Central Great Barrier Reef, Northern Great Barrier Reef? What's happening there? And then once we have a better handle on the natural trends, to try to relate those back to fundamental biological processes, the benthic carbon fluxes, and what's driving these trends in carbonate chemistry. And ultimately, the goal is if we collect enough data and we try to constrain these relationships to feed it into models, to be able to integrate the physical, chemical, and biological components of variability on a reef to try to calibrate and test models of carbonate cycling in a coral reef environment. So the study site that I chose to address some of these questions is Davies Reef, which is an open lagoonal reef that's in the mid-shelf in the central Great Barrier Reef. It's located about 90 to 100 kilometers off of Townsville's coast, so it's fairly accessible in comparison to some other outer shelf reefs. And it's also, because of its proximity to Townsville, served as a bit of a historical test bed. So it's a very well-informed reef in terms of historical data, which helped contextualize this study a little bit. The reef itself is 6 kilometers long and almost 3 kilometers wide, so I did have to focus in on a more tangible study site, which is this 300 square meter approximately area of the reef flat that's enlarged here. And this was strategically chosen for a couple of different reasons. Firstly, it avoids these false crests that are predominant on the rest of the reef crust, and that complicates hydrodynamics. And then also because this is the exact same portion of the reef flat that Dave Barnes studied in the 70s and 80s, so it was to try to facilitate a bit of a historical comparison. On this area of the reef crest, the currents are they're determined by a combination of winds, tides, and surface slopes. So if the winds are below 10 knots, they're predominantly driven by tides. And we get tidal reversals that are slightly counterintuitive. They actually flood from the lagoon to the crest and ebb from the crest to the lagoon, which is important later in the talk. So I went to this site twice last year, in summer and in winter, January and August, to try to facilitate a seasonal comparison. And both times we were there, I used a combination of fixed stations and transects and a variety of different sensing equipment and methodologies to try to characterize the physical, chemical, and biological components of this study site. So in terms of physical data, we deployed acoustic wave and current meters, or AWACS, off the reef slope to characterize the wave activity of the incoming water mass. We had ADVs that were situated on the reef flat itself and back towards the lagoon to get current speed and direction, light sensors, depth, temperature, salinity. And then the chemical side of things, these are automated water samplers that I developed at Ames with the engineering workshop that will collect discrete samples of water at whatever interval you program them to. So we programmed them to collect water at 2-hour intervals over the entire deployment. And they collect into these shot bottles that can be analyzed for total alkalinity and DIC back at Ames. And those two parameters are then used to calculate pH, PCO2, saturation state, and carbonate. And then because we're interested in tying this back to the benthic community, we did benthic surveys to estimate percent cover of various functional groups, corals, algae, CCA, sand, etc. So just to touch on the fixed stations first, I already mentioned the water samplers. So the first time we were out there in January, I only had one built at that time, and it was deployed in the protected side of the reef flat to minimize damage to it. So it's on the lagoonal edge, and we obviously deployed it there again when we went back in August. We just added more at that point. And it collected discrete water samples every 2 hours for a 10-day period in January and a 10-day period in August. And this is just an example of the type of data that you can get from it. I'm not going to go through it in detail now because I'll revisit it later. But this is the 10-day period in January, so you can see those clear Diel oscillations where you're getting a drawdown in DIC over the course of the day because all of your photosynthesizers are taking up the carbon dioxide during the day. And you get a minimum of DIC or a maximum of pH right around dusk. And then after the sun sets, you switch towards respiration and you get an increase in CO2 throughout the night and a corresponding decrease in pH. And your minimums in pH and maximums in CO2 are typically before dawn. So to tie this back to the biological activity, we really wanted to measure net ecosystem calcification and net community production because these are the two primary drivers of the coral reef carbon cycle, organic and inorganic carbon metabolism. And there's a variety of different ways that you can do this, slack water approaches, enclosure techniques, mesocosm, flow respirometry, etc. So this is an example of an enclosure technique called the SHARC, or the Submersible Habitat for Analyzing Reef Quality, that was developed by Kim Yates at the USGS in the United States. And this is an example of the Lagrangian approach. This is actually us. This is actually Ben. And this is the approach that we used on Davies Reef. So flow respirometry is an approach that was developed in the 50s and was applied to streams and rivers to measure production upstream and downstream, and then calculate that or translate that into a rate. And it's been adapted to coral reef environments that typically experience unidirectional flow during incoming or outcoming tides. So that goes back to the tidal reversals, that we had this opportunity to do it several times during the day when the tides were changing. And essentially what the technique consists of is tracking a parcel of water, which you can either do with fluorescein dye or with a drogue. And then you measure a chemical constituent of interest, which was for us total alkalinity and dissolved inorganic carbon upstream of, and then you follow the parcel and continue to sample, and then you measure it downstream of your community of interest. And you have your difference in your chemical constituent and your transit time that you can produce a rate at which the underlying community alters the chemistry of the overlying water column. So these are the actual mathematical equations that you use to produce these two numbers: net ecosystem calcification, which is NEC, or calcification here. And then this is net community production, NCP. The first equation is just the second equation rearranged. So in most coral reef systems, it is thought that changes in total alkalinity are really only caused by calcification and dissolution. And so if you have your change in total alkalinity, sorry, I should say that it's in a predictable fashion that for every mole of calcium carbonate that's secreted or dissolved, 2 moles of total alkalinity are consumed or produced. And so you take your change in total alkalinity, 1/2 of that, correct it for your transit time. This is the water depth and the density of seawater, and you can produce a calcification rate, net calcification rate for a community. DIC, on the other hand, is affected by calcification, dissolution, and also photosynthesis and respiration. And so if you know your change in DIC and you've taken out the portion of that change in DIC that was due to calcification, what you have left over is the portion of it that was due to production. So this is DIC that was corrected for the calcification signal, corrected again for water depth and density, transit time, and this whole term over here is a gas exchange term, because when you're dealing with carbon dioxide, it can diffuse into the atmosphere or from the atmosphere to the seawater. So this is one example of one transect and what your results might look like. So this was a transect that was done on January 17th. It took about an hour to traverse the reef flat. And during that time, these were our initial samples, these are our final samples. During that time, there was a drawdown in alkalinity of 9 micromoles, 27 micromole drawdown in DIC. And then using the equations on the former slide, I converted that into a calcification and a production rate. These are examples of the dye that we use to track the water parcel, or the drogue that's used at night. And if you do this enough times, over enough times of the day, over enough days, over enough weeks, then you can produce a daily curve of calcification or production. So these are these are irradiance curves here. So this is net community production versus irradiance. I did 47 total in both summer and winter. And so this is the NCP versus irradiance curve and the NEC versus irradiance curve of all 47 of those measurements. So moving into the results, what we found was that seawater carbonate chemistry was highly variable over both Diel and seasonal timescales, which we now would start to expect based on a lot of studies that are being done. So over here on the left, we have composite Diel figures. This is time 0 to 24 hours, and these are different carbonate chemistry parameters. So the top is pH, PCO2, aragonite saturation state, dissolved inorganic carbon, and alkalinity for both summer and winter. And over here on the right, the table has the means and the ranges for summer and winter. And so you can see pH varied anywhere from pre-industrial values of 8.2 to future ocean acidification scenarios of 7.9. PCO2, similarly, pre-industrial values of less than 280 up to 540 parts per million or microatmospheres. There's also a seasonal signal. So we had slightly higher pH in winter than in summer, which corresponds to slightly lower PCO2 in winter and in summer. And seasonal differences are a result of differences in biological activity at different times of year driving that signal, and also physical forcing. And so to try to tease out what was really driving that seasonal comparison, we temperature corrected the data to look at how much of that change was physical forcing. And about 47% of this 0.06 pH unit change, 47% of that and 35% of the PCO2 change are due to temperature alone. So the fact that it was 28 in summer and 28 in winter. So physical forcing can have a huge impact on your seasonal shifts in carbonate chemistry. Diel carbonate cycles were primarily driven by net community production. So on the left here, we have the lower left is net community production as a function of time over the course of one day. And this dotted line is the aragonite saturation state. So you can see that during the day, as your net community production values increase, your saturation state value increases, which then feeds back in the top to higher rates of net ecosystem calcification. So NCP and NEC are very closely coupled, and that can be observed here in the correlation on the right. So this figure shows a daily time series of aragonite saturation state in both summer and winter. And the light and dark cycles are indicated by shading. And then this light gray line at the back is the tidal height. So, excuse me just a second. Oh, hey. So what's interesting by plotting it this way is that the phase of the carbonate cycle chemistries really seems to be driven by that light-dark cycle in your net community production. But the amplitude of that signal can be influenced by a variety of different factors, and that has to do with what your benthic community composition is, if there's a very strong signal, if it's a dampened signal, what your tidal regime is and your water residence time. If you have a deeper water column, you get less of a signal than a very shallow environment. If you have a longer residence time, the water gets to hang around a lot longer, you get a stronger signal than very fast-moving currents. So that amplitude is influenced by a lot of things. And the effect of the tides on the amplitude was particularly visible in this winter session. So we had mixed diurnal tides, semi-diurnal tides, where you have a strong tide followed by a smaller mixed tide. And you can kind of see that in the carbonate cycling, that during the larger of the two diurnal tides, you get a very strong swing in your saturation state values, and then the smaller tide that follows, you get a very small blip. It's a dampened signal, basically. So another way to visualize this data is by using total alkalinity dissolved inorganic carbon plots. And just to orient you a little bit here, the white vectors that are on it indicate the effects of different biological and non-biological processes on total alkalinity, which is AT, plotted on the y-axis, and dissolved inorganic carbon, or CT, which is plotted on the x-axis. So we have CO2 release or invasion, which is this horizontal white vector here, which if you get gas exchange just only affects DIC, it's not going to affect your total alkalinity. And then we have photosynthesis and respiration, which mostly affects your dissolved inorganic carbon, but there's a slight effect on alkalinity due to nitrate uptake or release. And then this one is calcification dissolution, or calcium carbonate dissolution, or calcium carbonate formation. And that goes back to the equation from before, where calcification and dissolution affect DIC, TA in a 2-to-1 ratio. So the slope of that line is 2. So the contours in the back here represent lines of constant saturation state. So if you plot your data points on this graph, if they fall directly on a slope of 2, the only thing going on in your system is calcification dissolution. If they fall on this slope of photosynthesis respiration, there's no calcification going on. So the slope of the line of your data points really indicates the balance between those two processes, which I think is all that says. So you would expect, this kind of feeds back into, there's an idea right now that coral reef communities may have the capacity to biobuffer or offset the effects of ocean acidification by elevating the saturation state during the day. So if your data points fall exactly along the slope of the isocleth, your biological activity is just going to move it up and down that isocleth, and it's never going to change the saturation state. But if the slope is less than that, then your biological activity will increase saturation state during the day and the opposite at night. And so that was true for Davies Reef, which is another way of showing the trends from the earlier slides, that you're really getting this strong biological signal that's altering the saturation state of the water during the day. And that slope is possibly going to be an indicator of reef function. There's a lot of workshops going on right now to figure out how to measure reef health and what would be valuable to measure reef health. And one of the suggestions is that including TADIC slopes may be an indicator of reef health because it shows the balance between calcification and production. And any sort of ecosystem significant stress event, if you had a bleaching event, if you had a phase shift from coral to algae, that would be expected to be reflected in that slope. Okay, so to touch on historical comparisons and comparing my work to Dave Barnes's work, firstly, historical comparisons are complex, mostly because there's a lack of baseline data. But if there is baseline data, they're also complicated by different advances in technology. So the way that we collect data today may not be directly comparable to how it was collected in the 70s or 80s. But regardless of that, there have been a few historical comparisons in the Pacific over the past few years. So one was conducted at One Tree Island, where Don Kinsey originally studied reef metabolism in the 70s and 60s and 70s, and then Jack Silverman revisited it recently. And he reported a 44% reduction in calcification over the last 40 years, and he attributed that to higher rates of nighttime calcification. But in contrast, in Kaneohe Bay in Hawaii, where Don Kinsey studied reef metabolism in the 80s, Katie Schamberger recently revisited that question and saw no change whatsoever in reef metabolism. And that was despite the fact that the saturation state values that Kinsey reported were much higher back in the 80s than what she was reporting today. So you would expect there to have been a shift, but there wasn't. So it seems to be pretty variable. Dave Barnes in the 80s studied Davies Reef, that same portion of Davies Reef. And my results are partly consistent with his. So he explained a lot of seasonality in his rates of reef metabolism. He attributed that seasonality in metabolism to shifts in the benthic community composition. So he actually saw algal blooms during certain times of year that influenced production rates that weren't there during other times of year. I measured benthic community composition both in summer and winter, and I didn't see a shift. They were comparable both seasons. And it seemed based on our sensitivity analysis of the temperature effect that most of the shifts in seasonality were due to physical forcing as opposed to differences in benthic community composition. But the actual calcification rates that were reported, he was reporting 16 grams of calcium carbonate per meter squared per day in summer and about 12 in winter. And I had comparable rates in summer, slightly lower in winter. I'd like to continue this study just to have more data points and see if that really is a true depression in winter compared to what he reported. But it looks like while some reefs may be quite heavily affected over time, as you would expect, others might be less affected. So back to the question of thresholds. We did have a go at this, at estimating thresholds, and when the reef flat system transitions from a state of net calcification to net dissolution. And we did this by doing linear correlations, but with net ecosystem calcification and saturation state in both summer and winter. Pearson's correlations, and they were significant. So there was a significant correlation between calcification and saturation state in both seasons. And the slope of the line didn't change between seasons, which is consistent with other previous studies. So on this graph, where the trend line crosses the y-axis, that saturation state would indicate when the reef flat community is transitioning from net calcification to net dissolution. And those numbers are 3.4 approximately in summer and 3.2 in winter. If you plot those values on the graph that shows the diurnal oscillation in saturation state, so these are the red lines here are the threshold values that were calculated over here. You can calculate that according to those thresholds currently, the reef flat is spending 29.6% of its time below that threshold in summer and 14.1% of time below that threshold in winter. Now, this is not an exact science because as you notice the R-squareds up here, that only 25 to 27% of the variance in MEC or calcification is actually attributed to saturation state. So it's an exercise that a lot of people go through to try to estimate a threshold, but it should be treated with care. But regardless of what the actual threshold is, and I do believe that if I have more data and populate this more, that we'll get a stronger relationship because there's a lot of literature that saturation state very strongly controls calcification. But regardless, the take-home message is that even if you have these oscillations on the reef, the saturation state of the incoming water mass is going to be lowered, and that's going to be your new baseline. And then the reef is going to influence that mean value through biological activity. And so you would expect that the percentage of time that they'll be spending, that this line then is going, the average line is going to decrease because the decrease of the saturation state of the incoming water mass is decreasing. And then with ocean acidification, they'll be spending more time below that threshold and less time above that threshold. And it's just trying to iron out exactly what that threshold may be. So with that, I have a lot of people that helped with this project. Ken Anthony and Chris Langdon are both co-authors. We just submitted part of this work there are a lot of other components of this work that I didn't touch on today, but we just submitted it to Biogeosciences, so it's in review right now, but it's available as a discussions paper if you have any questions or if you want to go revisit it online. Ken Anthony and Chris Langdon are co-authors. I spent a lot of time talking with Don Kinsey on Magnetic Island about stuff that he did back in the 60s, 70s, and 80s. And then Ben, Carla, Steve, Emmett, Neil, Eric, and Paulina all helped me in the field and were incredibly invaluable. So thank you, and I will take any questions that you have.